In the electrified era of the hypercar, mass is the enemy, yet energy density is the only ammunition. Every manufacturer faces the same cruel equation of physics. To generate record-breaking power, you need massive battery capacity. To carry that capacity, what you add immense weight. And to manage that weight, you need a chassis rigid enough to handle the load without twisting into oblivion. Most builders settle for a compromise. Rimac chose total integration. Now let's open the factory blueprints and deconstruct the story of this engineering titan. When we analyze the foundational architecture of the Nevera, we immediately notice the absence of the industry-standard skateboard layout, a flat battery pack simply bolted underneath the floor. For a machine designed to deploy 1,114 horsepower, a bolted-on plate acts merely as dead weight, a parasitic load that actively fights the car's dynamics. The engineering challenge here was not simply storage, but structural survival. The torsional forces generated by 4 independent motors vectoring torque at the limit are violent enough to shear conventional chassis welds. Rimac's engineers realized that a separate battery pack was a structural liability. To achieve a target torsional stiffness of 70,000 Newton meters per degree, a figure that eclipses dedicated Le Mans prototypes, they had to invert the problem. They couldn't just build a box to hold the energy. The energy source had to become the backbone of the car itself. By rejecting the flat floor in favor of a complex, T-shaped spine positioned behind and between the occupants, they optimized the polar moment of inertia. However, this decision created a manufacturing nightmare. The requirement to package a massive energy store into a structural monolith capable of keeping the driver alive. Entering the temperature-controlled clean room at Rimac's Jankomer facility, we leave the realm of standard automotive assembly and enter a process closer to aerospace fabrication. The solution to the structural problem lies in the precise choreography of 6,960 individual components. These are 21700 format cylindrical cells, lithium manganese nickel chemistry, chosen for a specific volatility to power ratio. While the cell format itself is an industry standard, the methodology of their integration is where the engineering diverges radically from the norm. The manufacturing hunt here was defined by a single, terrifying thermal reality. Discharging 1.4 megawatts of power generates heat intense enough to trigger thermal runaway in seconds, if not evacuated immediately. When we inspect the module assembly, we see that Rimac rejected simple air cooling or basic bottom plate cooling. Instead, they developed a complex, vascular system. Engineers designed thin, S-shaped cooling plates that snake between the radial rows of cells, maximizing surface area contact. This is a manufacturing headache of the highest order. The tolerances required to sandwich thousands of cells against cooling ribbons without crushing the casings or leaving air gaps are measured in microns. Every gap is a potential hot spot. Every hot spot is a performance throttle. The assembly process groups these cells into modules, but the battery pyramid concept relies on what happens next. The modules are not merely bolted into a casing. They are structurally bonded. A specialized potting compound is injected, solidifying the thousands of independent cells and cooling channels into a singular, rock-solid mass. This is the critical manufacturing pivot. By turning the battery modules into a monolithic brick, the engineers transformed a delicate energy store into a load-bearing component. This brings us to the architecture of the H-spine. Rather than a flat slab, the pack is sculpted to fill the central transmission tunnel and the space behind the cockpit. This shape is notoriously difficult to manufacture compared to a skateboard deck because it requires varying module heights and complex coolant routing that fights against pressure drops. Yet, factory analysis shows this configuration is non-negotiable for the vehicle's physics. It concentrates mass in the absolute center of the car, reducing the polar moment of inertia to make the vehicle rotate faster. The final stage of this manufacturing hunt is the marriage of the pack to the monocoque. This is not a drop-in installation. The battery pack, now capped with a carbon fiber lid, is bolted directly to the carbon tub using huge titanium studs. It does not sit in the chassis, it completes the chassis. When the torque wrenches click on those final fasteners, the battery pack closes the structural loop, increasing the torsional rigidity of the carbon monocoque by 37%. We are witnessing a manufacturing process where the power source acts as the keel of the ship, creating a singular unit that is stiffer than the chassis of an LMP1 race car. The operational reality of this structural fusion is a vehicle that defies the traditional sluggishness associated with heavy electric platforms. When we analyze telemetry data from track testing, the significance of that 70,000 Newton-meter per degree stiffness figure becomes clear. It is not just a number on a spec sheet, it is the foundation of mechanical grip because the chassis refuses to flex under load. The suspension geometry remains perfectly consistent, allowing the tires to maintain optimal contact patches even during high G cornering. This architectural decision has established a permanent legacy in the philosophy of electric performance. Rimac proved that weight, while unavoidable, can be manipulated. By abandoning the skateboard layout for this H-spine configuration, they demonstrated that an EV does not have to be a NUSMI rolling platform. The battery is no longer passenger cargo. It is a stressed member as vital to the car's integrity as the engine block was in a 1960s Formula One car. This effectively renders the distinction between fuel tank and chassis obsolete. Future hypercars will not carry their energy. They will be built out of their energy. As we watch the Nevera blur into the horizon, we realize the true marvel isn't just the raw speed, but the silent, rigid unity of the structure beneath it. It is a testament to the mind's ability to turn a burden into a backbone, proving that when facing the immutable laws of physics, engineering does not compromise. It adapts, it integrates, and ultimately, it ascends.